Hello everyone, welcome back to another video. Today we'll be covering composite functions. So what is a composite function? A composite function is when you substitute one function into another function. Okay, let's say we have this. We have f with this little circle, gx, or we can simply write it as fgx. What this means is that you are substituting gx into fx. You're always substituting the inside function, in this case gx, into the outside function, which is fx. Now it's really important to note that fgx is not the same as gfx. What gfx is you're substituting fx, which is the inside function, into gx. Okay, let's try out the first example. What is fgx? So we are putting gx, we are substituting gx into the x of fx. Again, we are substituting gx into fx. So we're replacing x in fx over here with e to the power of x minus 1. So this will get us e to the power of 2x minus 2 plus 2. Next, what is gf3? What this is trying to say is we are substituting f3 into g of x. So what is f3? f3 is actually just 3 squared plus 2, which is 11. So this is the same as saying g11, which is equals to e to the power of 11 minus 1. This is e to the power of 10. Another way of doing this is finding out what the function gf is. So gf is just substituting f into g. So we're substituting this into the x of g. So what this gets you is e to the power of x squared plus 2 and then minus 1, or e to the power x squared plus 1. Substituting 3 into the function gf will be equals to e to the power of 3 squared plus 1, which is also e to the power of 10. So to recap, there are two ways of solving this. First of all, we can find f3 and sub it into gx. Or we can find the function gf and then substitute in 3 into gf. Both of these work. Alright, let's try our question. Fx equals to e to the power x, that's your expression, and x is more than or equals to 0. So that's the domain of fx that they gave to you already. So let's follow this domain. And gx equals to 1 over x minus 1, where x is not equals to 1. Find the domain of gf. So actually the domain of a composite function will be equals to the domain of the inside function. So the domain of gf will be equals to the domain of f. But we have to account for restrictions. Okay, what does that mean? Let's first try it out. Okay, domain of f is x is greater than or equals to 0. So let's find out what gf is, okay? Gf is actually just substituting this into this x. So that will give us 1 over e to the power x minus 1. So what do I mean by accounting for restrictions? So for example, for this, the restriction is that e to the power x minus 1 cannot be equals to 0. Another possible restriction is, for example, if I give you a function x plus 2, do you know that x has to be more than or equals to negative 2 for the function to be defined as real? Okay, so that's what I mean by accounting for restrictions. So we have to account for the fact that e to the power x minus 1 cannot be equals to 0. So e to the power x cannot be equals to 1 and x cannot be equals to 0. This means that the domain of gf is just x is more than 0. We cannot include 0. Okay, so now we know how to find the domain of a composite function. But how about the range of a composite function? Let's say we have fx equals to e to the power x squared, where x is more than 0. Again, a little bit of recap. E to the power of x squared is like this, and it's not the same as e to the power x squared. Okay, this is equals to e to the power 2x. So these two are two completely separate things. And gx equals to 1 over x plus 3, where x is not equals to negative 3. So find the range of gf. So the first thing I want to do is find out the range of f. Because if we find out what the range of f is, and we substitute this into the x of gx, we can find out the range of values that GF will actually produce. Usually my two biggest clues for the range will be the domain and any maximum points. Okay, for the domain, let's say I have a graph, something like this, right? And this is where x equals to 0. I can find the range easily by just substituting the starting and the ending points. So that's how the domain can be very useful for helping to find the range. But sometimes you can't just substitute the starting and ending points. In the case of such a function, we actually need to find a minimum point. Because if we substitute just the starting and ending points, we will get this. But we will not get this range of values of y that are actually valid. Okay, so let's look at this function, e to the power x squared, where x is more than 0. Actually, we don't have to worry about minimum or maximum points, because if you look at this, right, the function just grows and grows and grows and grows. It keeps increasing and increasing. This is what we call an increasing function. Since there are no minimum or maximum points for this function over here, we can just safely substitute the domain. So let's see, f0 will just be e to the power of 0 squared, which is 1. Okay, and then we'll substitute the other endpoint, which is when x is approaching infinity. So as x approaches infinity, we also see that fx approaches infinity. Okay, so we can safely assume that the range is just y is more than 1. From what we substituted over here, we can kind of predict the graph to look like this, where it keeps increasing and increasing to infinity. And at this point where x equals to 0, y equals to 1. So the range will just be y is more than 1. Again, to find the range without a GDC, what I like to do is use the domain, the endpoints of the domain to help me, as well as use any minimum or maximum points. Okay? Now that we have our range of f, let's find out what GF is. GF is just substituting fx into this x over here. So we'll get 1 over e to the power of x squared plus 3. Okay, let's look at our range of values of f. We know that this thing over here, which is f, can only be more than 1. So again, I'll look at this to help us find out what the range of GF is. So we look at the endpoint when fx equals to 1. When fx equals to 1, this is basically saying that fx is 1, which is equals to 1 over 1 plus 3, which is 1/4. And if you see, right, if you look at this, as fx approaches infinity, so as it passes 1 to 2 to all the way to a very, very large number, let's say a very, very large number near infinity, right, what happens to gf of x? If you look at this, as fx approaches infinity, we can write that gf of x, look at this, if we put in a very large value, it will actually basically be equals to 0. So we can say that as fx approaches infinity, gf of x approaches 0. It gets smaller and smaller until 0. So we have these two key pieces of information here. g1 is 1/4. gf of x decreases all the way until 0. So by this, we can say that the range of gf will just be y between 0 and 1/4. Take note, since fx is more than 1, strictly more than 1, this means that it has to be strictly less than 1/4 over here. See, 1/4, it cannot be equal to 1/4, right? And the other thing is that since we can only approach infinity but never equals to infinity, this means that we also have to have strictly more than 0. Okay? And this question over here, even though it's quite a difficult domain and range question, this is a 2-mark IB question that actually appeared in IB. So again, to recap, to find the domain of a composite function, the domain of gf will be equals to the domain of the inside function, but you have to account for any restrictions. For example, over here, if you have gf equals to 1 over e to the power x minus 1, we have to account for the restriction that the denominator cannot be equals to 0. The next one, when we want to find the range of gf, or range of a composite function, we first find the range of the inside function. In this case, we find the range of f. By finding the range of f, we know the bounds of f, which helps us to find the range of gf. Hopefully this video helped you understand how to find the domain and range of composite functions a little bit better. It's always very important to keep practicing.